Okay, so are you ready? We can start this. We can start this second presentation about the Metafor tutorial. So the idea is to go through this presentation and start from what we did last time. Yes, okay. So we reached. So we were on the section 3, and the geometry. Section 4, actually. Yes, so the geometry was done. Okay, yes. So if you remember well, we created points, then lines, then wires, contours, and then sides to define the geometry. And in the memory, there was this Metafor object, which was linked to a domain object, which also contains a geometry object, and this geometry contains a point set, curve set, a wire set, and a size set. So each time if you have, let's say, Metafor, or any of these objects, you can have an access to an object that is below by a get method. So if I have the domain, if I would like to have the geometry, I just type domain dot get geometry, and I get a pointer to that geometry, and I can assign a variable which is usually called geometry. So now we have our geometry. We must create a mesh, and then put some finite elements, some large deformation elements on this mesh. So in order to use the geometry as support for the mesh, we can define meshers. So it's exactly the same as before. Everything in Metafor is defined in classes. So there are objects which represent meshers. So if you have a line, here the line number 1, you can create a simple mesher 1D. That's the simplest mesher that is available, with just distribute nodes along the line. And the syntax is an object-oriented syntax, so it means that this first part of the command creates a mesher on curve number 1, and then we execute the execute command of that object by the dot, then the name of the command, dot execute, and then some arguments. Here, the arguments is just one integer, which is the number of nodes that you want on the curve. No, it's the number of segments. Sorry. All nodes. I don't remember. I think it's the number of segments. So first we need to mesh the 4 sides, the 4 edges of our cube, and then we can use a 2D mesher, which is called the transfinite mesher 2D. And this kind of mesher just make links from meshed edges. So if you have edges that are meshed with the same number of elements, you can just use the transfinite mesher to make a mesh which looks like a chessboard, actually. So it's a regular mesh of quadrangles. If you want more more elaborated measures, you can have a look at the documentation, and here you have a link to the web documentation where several kind of measures are available, but actually in most cases you will use this one, because you see that if you take the time to divide your mesh in things, in parts of geometry that can be meshed with this measure, the resulting mesh is very clean. It's so you will have elements that are almost, well, all the main lines of your mesh will be perpendicular. You will have squares or rectangles, and you have seen in your finite element class that this kind of shape lead to the most accurate results. So usually you do not want Metafor to put elements in a completely random way. But there is a way to create unstructured meshes, and you can have a look at it when you have very complex shapes in 2D. So once your model is meshed, yes, just one remark here about the orientation of the mesh, actually. The elements have an orientation, and this orientation is usually counterclockwise. It should be counterclockwise. And this orientation is inherited from the wire. So the wire has an orientation, and the elements have the same orientation. If you create a wire which is oriented in the wrong way, all your elements will be oriented in the same wrong way, and so it will lead to what negative areas of your elements. And in Metafor, it means that the Jacobian of the elements will be negative. So the mesh will look perfectly nice, but all your elements will be inverted. So be sure that your wires are in this have this orientation. So next, it's interesting to see how to link the mesh, which is just a grid, with the physics. Okay. And so for example, we can define materials. Materials are related to all the constitutive laws that some of you maybe have already seen in the advanced solid mechanics class. So for example, here I define an elasto-viscoplastic material, which is hypoelastic also. And defining a material means having access first to the material set. So it's again the same thing. You take an object and then you grab the set related to the object that you want to create. So here you must know that the material set is inside the domain. And then from the material set you can define a material. So this is the name of the material, and here you can have access to the documentation. Almost half of the documentation is about materials, because many PhD theses, many final year projects in Metafor are related to just the creation of new materials. So there are many materials, many behaviors, and this is the simplest nonlinear one. It's an elastic one, and once the yield stress is reached, there is some plasticity. The plasticity is isotropic, and the hardening of the material is linear. But there are many, many other ways to define more realistic materials. But of course, in your model, just start with this material, because it should work. And in order to to set all the properties of your material, you have this put command, which takes a material. So take the material set, you grab the first one, which is this one, and then you put a name and then a value. And for each material, you have a list of properties that should be filled. So for this one, you have the density, you have the elastic modulus, you have the Poisson ratio, and then you have a number related to the hardening law. So here also a remark about the units. I don't know if you have used a lot of simulation codes in the past. So there are no units in Metafor. So it means that you can choose any unit, but everything should be consistent. So for example, if you choose, if all the length of in your input file are written using millimeters, then and you use this kind of properties. So you see here that you should, in order to write these numbers, you have made some assumptions about the units. So in this case, forces are in Newton, stresses are expressed in Newton per the same unit used for the length. And then you can just make a dimensional analysis of the equation. Your density should be in ton per millimeter cube. So be careful, because some students just use meters here, for example. Then if the forces are in Newton, the stresses will be in Pascal, not megapascal. It will be in Newton per meter square, because the unit used for the length is the same in your geometry and in your, for example, elastic modulus, which is expressed as a stress. So the next thing is this one here. So you have materials, but materials can be connected to many other, what we call laws. So it means curves that describe the evolution of some variables. It could be, for example, here the hardening of the material. So in order to define a linear isotropic hardening law, you must create a material law, which is described which is stored in the material law set, which is next to the material. So here it's the material set, and then next to it you have the material law set. So you have several materials, several laws, and each material can choose in curves from the material set. So thanks to this system, you can combine different behaviors with different, for example, plasticity criteria and so on. So once again, all these commands, all these names for the hardening laws, for example, are in the documentation. So the next step is to define element properties. So once again, it should look. It looks maybe a little bit complicated, but you will have exactly the same step in your model. So here I explain the details, but in practice, try to remember the details. But the first thing you will need to do is just to copy paste or start from the tutorial and modify it, so that your first model just use these for example, element properties or material properties, and then when it works, you will try to change the material so that it fits exactly what is inside your paper, for example. So you have materials, material laws, and then finite element properties. And what are these properties? So for example, here I define a material. So I say that my elements will have the material number 1, and I also define a way to integrate stresses. And it's maybe a little bit early for the moment, but you will see later that there are the finite elements that are defined in the large deformation theory have several problems. And one of the problems is called locking. So it means that the stiffness of the element is too large. And there are several ways to deal with this problem. And one way is to make more elaborated integrations or under integration of some parts of the stress tensor. So you will see this in theory. And so in practice, you have several ways to integrate stresses. And all these ways, there are three or four ways, lead to a specific stiffness, which is good, bad, or the best stiffness that you can expect from one element. So the next step is to define a field applicator. So what is this? So that's an object which links the geometry with your property. So I can maybe try to display here. So you have your mesh. Hope it will. Okay. So that's just a grid. Okay. So that's what I call the geometry with points. And then you have a material law. In the material, you have a link. You must say that my material is linked to this material law. You have an element properties actually, which says my elements have this material, and then you must link your geometry to these three objects. Okay? So this is done with the field applicator. So you create one object like this, and you just say, I will apply this kind of element onto this geometry, this mesh. Okay? So So you see here, this field applicator, number 1, links the geometry, the side 1. Side 1 is your square, with the property. And the property is linked to the material, which is linked to the material law. So everything is linked. And what makes the link is this field applicator. So this, yes?
You are not going to record the course?
Yes. Yes.
Okay.
So it is recorded for the moment.
Okay.
So as I said, it looks complicated, but it's always the same. And here we are going to define contact interaction. So we need to define some contact between our punch and our mesh. And this is exactly the same as we have done for the cube, for the material which is inside the volume. So we need a material, we need some property, and we need something which links this property to the geometry. And this is called, in this case, not a field applicator, but a contact interaction. So all the contact behavior, all the physics of your contact. So for example, the friction, but also all the numerical parameters are stored in the material in Metafor. So for the contact. So if you have some steel, you will put your Young's modulus in the material, and your hardening in the material. But if you have contact, you have some friction coefficient. It's also put in a similar contact material next to the steel material. So this is the contact material, and as all the materials, you have a list of parameters that are always the same. We just give values to the parameters that are needed by the material. We have element properties, which links the finite element to the material, and you have some options. Remember that for the volume, we had some options about the integration of stresses. Here we have some numerical options, which says if we update the length of the contact elements when we compute the pressure. That's a detail. You will see this in the lecture about contact during the class. So a material, an element property, and then something which links the geometry and the property. So here you must say, I have a punch. So let's go back here. I hope it will work. So I have a punch. I have some material. I must create a material, a property, and then I must say, I must create a contact interaction which takes the geometry. So here the geometry is the lines that will be in contact. So you have this line and this line. They can be in contact. And also, you must make a link to this, because there is also a link to this. So that everything in the tree that you have to see at the beginning of the presentation is linked. So here for the contacts, last week I talked about the orientation of your tools. So you see that if you have a rigid tool like this, it is just defined by one curve. It could be also one wire, but the orientation has a meaning. If the orientation of the curve is like this, it means that I have a punch, the material of which is here in blue. If the orientation is in this way, it means that the material is there. So you see that for this particular problem, you must choose this orientation, or otherwise the problem has no meaning. So here it would be okay if you had some, for example, a ball or anything which could bounce inside a hole like this. Here you have a punch, so the orientation should be like this. So in order to see the orientation of your tool, you have in the graphical user interface some options that can be activated to check the orientation. So you will have a green area and then a red area around your tool, and so the contact will occur between the red area and your mesh. So it means that if I had this green area red, it would be impossible, because at the very first time step I would have the red area and the mesh over each other. And one particular numerical parameter, which is rather important, is called prof cont. So it's in French, it's profondeur, it's depth. So it's the contact depth, which is the size of this. So that's the depth of this this area. So here I can also make some drawing, because it's not very easy to understand. So, okay. So if you have a tool like this, and then some mesh that can go into contact with this tool, you must understand how contact works, but you haven't had already the lecture about contact. So how does it work? So you have a tool, you have a mesh, and the method is called the penalty method. So it means that at a particular moment, your mesh can be inside the tool, because you have seen that Metafor computes the equilibrium by trial and error. So it means that the configuration of your mesh changes iteratively in a Newton-Raphson procedure, and it is corrected as long as the equilibrium is not reached. Okay, so at a particular moment, while Metafor tries to reach the equilibrium, you can have one element, well, this kind of configuration, which is obviously not correct, because your tool here, well, you have some nodes, and well, your mesh here is inside your tool. So how does the method works? So here you have your contact elements. The contact elements are nodes, and the idea is that the nodes on the line that you have given to your contact interaction are not allowed to go too deeply inside the tool. So it means that at this particular moment, Metafor will try to project all the nodes, all the contact nodes. So this is perpendicular. So it will compute projection of all the nodes, and Metafor will also compute the sign of what is called the gap. So thanks to this orientation, there can be a normal, which is uniquely defined thanks to this orientation, an outer normal, And so I can say that this gap, this is negative. This gap is negative. This gap is positive. This gap is positive. And the idea is to create a force. So Metafor will create a force which will act on each node that has a negative gap, which is proportional to this gap size. So it's as if you had a spring, which is like this, between the nodes that have penetrated into your tool and the surface of your tool. And so Metafor will just create forces. And so the nodal forces, so the force will be some coefficient P times the gap G. And this is called the penalty, so that's penalty coefficient. So that's the stiffness of your contact. So it means that you would like to have the largest stiffness so that the node will have a very large force if the contact constraint is violated. So the best value is, let's say, plus infinity. So that the force, each time the node crosses the boundary, a force in this direction will be created, which is infinite. So that jumps out of the forbidden area. But of course, with this kind of value in a numerical code, nothing works. So you must choose very high numbers. So for example, 10 to the power 6, for example. So that's what was in the material. I will show you before the slide that I showed before. But there is also another problem with contact. Imagine that you have, so where am I? Yes. So we have exactly the same algorithm, but we have something like that. And a node is, let's say, it is lost here. You see that there is a problem because you have many projections possible. Maybe here. So you have several projections. So the direction of the force is undefined. And this is because you have something which looks like a nail or... So the idea is to say that the node should stay close to the tool. And that's where this contact depth comes into play. So here you can imagine some, so I will use the French word, so prof as profondeur, so that's the depth. And imagine that you have some kind of thickness of your tool. You know that if the node lies into this area, this red area, there is only one projection. So it means that here, well, you don't have any the projection is here. Here, the projection is here, so everything is okay. So this parameter is important to solve these multi-projection problems. But you need to give a value to that number. So this is a numerical parameter that is left to you. So usually what do? We choose this parameter as the smallest radius in your model. So if you have, let's say, one line, one circle, and then one line. So this is the radius, the smallest radius. So the contact depth should be less or equal to r. Otherwise, if it's here, you could have multi-projections. So that's the main parameters of contacts. The first one is this penalty, P, and the second one is this depth. So let's go back. The presentation, yes. So one way to visualize this depth, the depth that you have put into your input file, is the thickness of this area. And there is also this green part. So in this green part, the nodes are projected and tested if they are red or green. But if the nodes are outside, they are not projected at all. So it is important to have a depth that is not too large. Otherwise, all the nodes are projected. But it should not be too small. So it really depends on your geometry and on the problem. So that was contact. So the next step is to define boundary conditions. Boundary conditions are mainly prescribed displacements. So you want to fix some nodes at some given locations. And the syntax is a little bit obscure, maybe, but it's, well, just copy-paste the line. So the boundary conditions, such as these ones, are defined in an object which is called the loading set, with the command define. And this command takes one curve. So here, that's the curve 1 and 4. A direction. So here you have the x displacement. Well, the name of the x displacement in Metafor is this strange thing. And then the value. So here it's 0. So we just prescribe 0 on these two lines. And we use exactly the same kind of commands to prescribe the displacement of other entities, such as the tool. So the tool should be moved in the y direction. So it's y here. The tool is curve set 5. And when you move something, so when it's not 0, the final displacement is the product of these two factors. So you have a scalar, which is here minus d. D is just a variable, times a function. And this function translates the dependency as a function of time. So here I have defined a piecewise linear function with the coordinates 0, 0, t1, 2t, 0.5. So I have this curve. Imagine that the x-axis is actually the time. The y-axis is the value of the function. And the final displacement at a given time is this function times d. So this product is a way to use several times the same function so that you can prescribe different displacements that are just the same as, with a different factor. So one of the last steps in the input file is the time integration. So as I showed you last time, each test case of Metafor is computed by increasing the time from, let's say, t equals t0 to t equals the final time. So you start from one time, here t0, you go to here t2, but you would like, for example, to have a control on the time step that is applied. You would like also to control the way which is used by Metafor to save archives to the disk. So you have seen that Metafor saves bfac.gz files, which contains everything at a given time step. So you would like to say, for example, between t0 and t1, I would like 5 files on my disk. So these files will modify the time step between t0 and t1. So for example, if you start from t0 with a big time step and you say I would like 5 time steps, save to disk, the time step will be decreased to 1/5 of t1 minus t0, so that at least 5 time steps will be done. So all these parameters are defined in a block like this. So at the beginning of the block you have an object which is the name of the time integrator, so the numerical scheme that is used to integrate so here it's an alpha generalized time integration. You will see several other time integration schemes. And from Metafor, you can have access to another object, which is called the time step manager, which prescribes some constraints on the time steps. So for example, here we say we start from t equals 0 with an initial time step of 0.01. Then we would like to make a first computational stage at t equals t1. So it's t equals big T here. Between these two times, we would like 5 files on the disk, and we would like a maximum time step of 0.1, because you will see that Metafor will adapt the size of the time step depending on the speed of convergence of the algorithm. So it means that if everything works well, so if Metafor makes just a few iterations to find the equilibrium, the time step will increase. But if something goes wrong, so if, for example, the equilibrium is not reached, so if you have some kind of divergence, Metafor will restart the step with a smaller time step. So it will divide and divide and divide and divide the time step. So the size of the time step will be very big when nothing happens. So if you have a rigid body motion, for example, the time step will increase, increase, increase. But if you have some contact, the forces that will be generated, you have seen that forces are generated from the contact, will be so stiff that the equilibrium will not be possible. So the time step will just fail, and Metafor will restart this problematic time step with a smaller time step. And then you will divide until it is possible to start to reach the equilibrium with a smaller time step. But you will see that in practice. So there are also other parameters, such as the residual tolerance. So I put this parameter, even if this number is the default value, because this is a very important parameter. So you will have to change it to see the influence on your input file. This is the difference between the internal forces and the external forces that is accepted for the equilibrium. So if once again you have a perfect value, you would like this difference to be 0. So because you want a perfect equilibrium, but numerically you will never reach 0. So the balance between the stresses, the internal stresses and the forces that are generated from these internal stresses and the external forces, so the difference will be close to 0, but never 0. So as Metafor tries to reduce this error, you must give a tolerance to Metafor so that he is able to say, okay, I have reached this difference, so the time step looks converged. The equilibrium is not perfect, but it's close to perfect. So of course, you can guess that if this number is very, very, very small, you will make a lot of iterations. So you will have a lot of small time steps, because when you make a lot of iterations, Metafor thinks it's very difficult to... there are some problems, so the time step will decrease. And if you increase this number, Metafor will make big time steps, but for each time step, the equilibrium will not be perfect. So you must, as for the penalty coefficient, you must find the best value, which is a compromise between the accuracy. The best value for accuracy is 0, but it doesn't work, and CPU time. The best value is, well, a very large number in this case. So one of the last thing, I think that's almost the last thing to put in your input file are the curves. So what is called the value extractors. So as I told you, you have two kinds of results in Metafor. You have these big files that represent everything on your mesh for a given time, but you could be maybe interested in the evolution of any value through time, so as a function of time. So if you save all your time steps to disk, it would be, well, you will fill your disk, and it will be very slow. So Metafor has this curve system. It's also available in most commercial codes, which consists in having a look at a particular place, a particular location on your mesh, and write to disk all the outputs, all the things that are calculated. So if you make thousands of time steps, you will have a curve which has thousands of values. So for example, this line extracts the time in a file. And this line, which has a special format, extracts the sum of the force, so that's the code for the force, on the curve one. So if you click on here on the documentation, you will see all the extractors that are available. So you can, for example, extract the contact pressures, the stresses along a line, the maximum equivalent plastic strain in your problem. So you have many possibilities. And here is a code that can be used to plot these curves while your input file is running. So you have seen that when I ran the tutorial, there is one main window with the mesh, but there is also another window which displays a curve during the calculation. So as you compute curves here, it is possible to add them to a window which is called viswin here. So you can just have some display of your results while you are testing your code. It's an interesting way to check everything. So that's all. So maybe it's a lot of things. And there many questions could remain. So I have gathered all the questions that I have received from former students into this final section. So you don't have to read it from A to Z, but I'm almost sure that you will have to check one of these questions. So there are 14 questions. So for example, how do I model my axis symmetric problem? Because the tutorial is in plane strain, and some examples are axis symmetrical. So how do I change the element type? So you will see during the class that there are several element types which have different properties. So it's important among all the parameters that you have to check that you use the best elements. Some elements are very expensive, so there is no. So usually accuracy has always a cost. So for all the parameters, including the element type, you will see that if you use the best element, the richest element, it will be very expensive. So it really depends on your problem, and you must choose your elements so that your model is not slow, but still accurate. I have a problem with element type XXX, so you will see that it's related to the theory. So some elements do not work in some situations. So for example, if you have axisymmetrical problem, some elements do not work well. If you have also a link to the material types. So for example, some incompressible materials do not work well with some element types. So for example, if you have an elastic problem, classical elasticity, you can use almost any kind of element. But if you have rubber, some hyperelastic material, some elements will not work. There will be some additional unwanted stiffness. That's the same for the plasticity. So plasticity introduces incompressibility because the plastic deformation is incompressible. So I want to mesh a more complex shape than a square. So almost all of you will have this problem because almost all the problems are not square. So we'll have to divide your side into things that looks like square, for example. This command acts on a curve, but I have several curves. So we have seen, for example, that I have extracted the force on one curve. But in your model, maybe you will have several curves, and then you would like to have the sum of the nodal forces on these sets of curves. So how do you do that? This command acts on a curve, but I have just nodes. So for example, I have my my cube, but I would like to extract the plastic strain in the middle of the cube. There is no line. How can I extract my strains in the middle of my mesh without any supporting curve? So my rigid tool is more complex than a single curve. So once again, your tool will be maybe a little bit more complex than just an arc of circle. Some problems involve contact between deformable bodies. So you have meshes that comes in contact with other meshes. It's almost the same as before, but there are some additional commands that must be put into your input file. Sometimes you want to prescribe a force on your tool. So imagine that you have your punch, and instead of prescribing the displacement, you prescribe a force. So it's not as easy as it seems, because the main unknowns in Metafor are displacements. So it means that the displacement of your tool will become an additional unknown of your problem. I want to prescribe an initial velocity or play with gravity. So some problems, in some problems, gravity is important, or you would like to throw something onto another, on a wall or something like that. So you must put an initial velocity. So the next thing here is, how can I find more examples related to a given command? So you will see that if you go into the documentation, you will have some examples, but maybe you would like to have an example which uses the particular command that you have found in the documentation. So for example, imagine that, so it's very small here, but you have found in the documentation that there is a way to model Coulomb contact. So it's a contact with some friction, with Coulomb friction. It's called Coulomb contact material. How can I just use this this material? I have no examples. Well, actually, that's the example of the tutorial. But imagine that you have another material which is not the same as the one of the tutorial. You can use this tool, which is called dngrep, to search through all the examples which are located in C program files metafor/apps, if you remember well. And thanks to this tool, which can be used in another context. So if you have a set of files, you would like to find all the files that contains a given keyword, you can use this tool. So that's the equivalent of the grep command in Linux, if some of you use Linux. So you can install this program and just put the keyword here, click search. here you must say that you search in this apps folder, and you will see all the examples which use this this given keyword. So you can run it, see what happens on your screen, and then have a look at how it is coded into the input file. So you have a working example for one command. In some, for some papers, you also have experimental curves or numerical curves, and maybe in your project you would like, at the end of the project, you would like to compare your curves with the curves from the paper. So one way to have nice pictures is to use this tool. Maybe there are other tools such as this one, but which allows you to take your paper and draw axes, then click on the curve and retrieve a list of coordinates. So even for your final year project, if you have several papers with curves and you don't want to scan and have a dirty figure and your results in another figure, you would like to have both figures on the same graph with very smooth and nice curves. This is the tool which will help you. So that's a detail. That's also a detail. Also another detail about how to have informations about commands. Also another way to see what happens in the memory of Metafor, but usually it's just for really advanced usage. And that's all. So if you have questions, so read the tutorial, read the frequently asked questions list, read the documentation. You can use Google search in the search box of the website. So if you type friction on the website, you will have a list of all the pages which talk about friction. You can use dngrep and have a look at examples. And also, yes, so next week and the week after, the idea is to come here with your laptop, work on your project. If you have any questions, I will be here to answer, to help you make your mesh and so on. So it would be interesting or very important to have a working model at the end of the second one, so in 2 weeks. So it's not difficult. So when I say working model, maybe the material will be wrong, maybe the geometry will be not perfectly correct. The mesh will be maybe a coarse mesh, which is very bad for the calculations. The time integration will be the one from the tutorial. The friction law will be the one from the tutorial, and so on. But something which runs, looks like your project, and which is a good basis for starting having a look at the physical content of your paper, of your problem.